Greetings, I welcome you all to the next lecture of this course. We will now be discussing on zinc dust. So in the previous classes, we have gone through lot many waste streams that are associated to zinc, and now we'll be focusing on zinc dust, and we'll be continuing this discussion in this class, as well as we'll be continuing it to some extent in the next one as well. It is important to note how really zinc dust is formed, and we'll be discussing some of the chemical compositions and how we are recycling it. So let us just start. We know that one of the most important ways of utilization of zinc is basically in the area of galvanization. So it's a crucial waste that is generated in the steel making unit. Actually, it is generated in the steel making process. So one might want to argue whether this waste really is a part of the zinc stream or the steel stream. So since it is having significant quantity of zinc, we can consider it as a waste stream of zinc because it is rich in zinc. The other way of looking at it is, since it is generated in the steel making unit, you could call it as a steel dust, EAF dust. So that is also one way of looking at it. Which is the way we would like to describe it is totally depending upon how we would perceive it. If we are looking at it from composition point of view, then of course we should go for considering it as a zinc dust. So it's generated in steel making industries, and this EAF dust or zinc dust, EAF dust some might want to say, and or the other common way of calling it is zinc dust, is really rich in zinc, and what normally happens is nearly about 10 to 20 kg per ton of dust is generated, per ton of steel is generated, and we'll see how much it really contains. EAF dust is basically generated when we have splashing, thin film splashing in the processing, right, during EAF operation. So when hot metal is getting splashed and this thin film splashing is happening, the fine dusts that are generated actually end up as EAF dust, and this thin film splashing is actually resulting in small size of the dust particles, because the larger particles will never end up in the dust, they will recede back into the hot metal. It's the final fine thin film particles that are actually removed because of the airflow convections, not the larger particles. The larger particles would really get reintroduced back into the molten metal bath. So this is the generation of the EAF dust. We'll now look at the chemical composition actually. For that, we'll just draw a table, and we must note that there are various categories of dust: the high zinc dust, high zinc, medium zinc, and low zinc dust. The chemical compositions are as such. We'll have types and elements. Types of dust. We have elements, of course, zinc, iron, some palladium, chromium, aluminium, and calcium. Of course, these are references that are present, and references are this general references. Just mention it like this. High zinc. High zinc is nearly 20% and above. Medium zinc is nearly 12 to 20%. Then there is low zinc, which is lower than 12% zinc. So we know that this broad classification is going to be with us. So we can assume that this breakup of the zinc dust is going to be according to these broad classifications. So we'll just have the internal divisions done. So high zinc we can have 22.26.66, 16.93, 2.71, 0.12, 0.59, 30.5, 27.6, 0.37, 0.12, 0.43, 2.1. Similarly, we have 51.6. So we can have a really large value here, 51.6, 16.5, 8.8, 2.0. So now we are looking at the medium zinc bracket. It can have 19.4, 24.6, 4.5, 0.3. Now in the lower zinc bracket, the low zinc, we can have as low as 5.2, 6.5, 19.37, 8, 1.4, 1.8, 10.9, 10.9. So we see that the breakup of zinc is really varying with the type of category that we are looking at, and the compositions of iron and zinc are the most important in these types of dusts, and apart from that we have other elements, chromium, aluminium, calcium, and other lot more other trace elements can also be present depending on what is the composition of the raw material that was used in the EAF itself. So what is being used in EAF will be coming out as dust. So apart from zinc and iron itself, all these elements can be coming up with the dust, and these are getting showed, these are getting observed in the EAF dust when we are characterizing it. So let's just mention some of the important references. Wang, Stewart, now when we know that these raw materials are fluctuating based on their composition, we can think of devising good strategies for efficient utilization of zinc from these dusts. Now, we know that these dusts are very fine in size, so one has to really think of how to utilize fine zinc dusts for as a raw material for their process. So, let us just look at some of the recycling ways, and before that we would also like to have a question: why recycle zinc dust? So we know the obvious answer that should come to mind is hazardous elements are present. Hazardous elements are present, let's say lead, tin, iron, chromium, etc. Hazardous, of course, iron may not be considered as hazardous, but of course the other elements that could be present, at times we can have mercury and cadmium also. So these types of elements, when are present, they can make the zinc dust hazardous, and these are detrimental to health. And of course one should be wary about how it affects the environment also. And we know that significant quantity is generated. In the production of steel, it's a significant quantity that is generated per ton. So one can think of reusing these wastes as a raw material. Now, how do we recycle it? Recycling. One of the ways is rotary hearth furnace. Rotary hearth furnace operation. What it does is basically EAF dust, or rather you could say zinc dust, is added with flux. So flux material is added, and you need coal, because it's a furnace and we can easily guess this is a pyrometallurgical operation. We are going to have flux with dust with coal acting as the agent for combustion, and it is going to give us some valuable materials. That is very easy to guess right at the beginning. What exactly happens is, we'll do mixing and we'll go for pelletization, because we know that the size of zinc dust is very small. So one has to go for agglomeration process. This is mixing and this is agglomeration, and after that we'll have the rotary hearth furnace, and the operation is going to give us DRI, HBI, hot briquetted iron, or you could say molten metal. At the same time, we have waste heat generation, from where waste heat generation and collection, which basically helps us in extraction of the zinc and other volatile materials. Zinc and other materials are separated. In this process. So what it normally does is, we take the hearth, we add the feed after of course pelletization, and it gives us the metal. And this process is actually targeting iron. The waste product in the form of zinc is getting extracted in the gas phase. So let us look at the second route. We have electric smelting reduction furnace. ESRF, electric smelting reduction furnace. So here again we are feeding it. We have the ESRF and it is going to give us metal and slag. The normal operation of a common furnace. What normally we should also be expecting is the combustion chamber that is attached to it and gas cooling. This is an important step. This step actually helps us in extraction of zinc, and this gives us back filter. These operations that are after ESRF, of course we are getting metal and slag, which is targeting iron and the iron related product. What we are getting beyond that is where we are where we should be looking at the zinc output. So here we are getting gas cooling and back filter give us ZNO extraction. ZNO extraction and separation. After, one should mind, after ESRF operation. This is very important because one might just expect we can just directly feed the raw material and get zinc. It is done only after the ESRF. ESRF gives us metal and slag, but the gas that is getting collected is actually processed elsewhere, and there you are getting zinc oxide. And of course we are still not getting zinc, we are getting zinc oxide. So one has to process zinc oxide and then get metal. The third route would be roasting for development of products. So another pyrometallurgical route of handling. What we can see here is we have EAF dust, EAF zinc dust, and we add F2O3, Fe2O3. We go for ball milling and briquetting. We have vacuum drying. And then we can have roasting. Roasting is done at a higher temperature, of course. And we can have leaching. Now this part, till this part we can consider that it is pyrometallurgical till this part. But now we are also introducing hydrometallurgy, which can of course give us nano bead milling of the finished products. So we can have nano bead milling followed by zinc ferrite. So what really zinc ferrite looks like: zinc ZnX, Fe3X, 3 minus X, and O4. Zinc is getting attached to the Fe3O4, and how does it really happen? It is followed after leaching, and you are doing milling one more time after that. So what these types of raw materials can be used for making zinc rich products that are of course attached to the iron component. So one has to add Fe2O3 to zinc dust, and then you can make these types of products. The other important alternatives for using zinc dust are basically hydrometallurgical, let's say leaching. Leaching with iron powder addition. And of course, iron powder is used as an additive here. It is not used, of course, it's not used as a reagent. One should really mind what we are adding when and what is its purpose. So we can have zinc dust, and of course zinc dust is coming from various sources, not just steel making. So one of the key areas where zinc dust can originate from is also from brass smelters, from lead zinc smelter also. So if we have zinc dust coming from lead zinc smelter, and such a smelter product is added with iron, it becomes a raw material, and this raw material we could be using as a feed for, let's say, leaching with H2SO4, and of course we are going for ultrasonication. What we can get is we go for the characterization of finished products, and we know that apart from the zinc leaching itself, zinc leaching from the zinc dust and addition of iron, it can also give us germanium recovery. So of course zinc is getting leached in the process, but germanium recovery is also reported by using such processes. When we are having different types of waste streams, we can have different types of finished products as well. Germanium recovery from zinc oxide dust. Now one more process would be reduction roasting and leaching. So we note that most of the processes really have to be connected to pyrometallurgy, and some parts of hydrometallurgy can be brought in. So if we have high zinc dust, it could be simply leached with water, and this is to remove dissolvable parts only and use solid residue for reduction roasting. So we have nearly 50% hydrogen at around 700 degrees Celsius. That type of operation can be done, and of course this has to be followed by leaching with acids. This is done, and then we can have leach liquor and solid residue. Again, one can use these types of raw materials for these types of products for making various types of raw materials. What this really means is you can have a wide range of applications connected one after the other, such that your raw materials are used properly. So in this case it is zinc dust. We've seen that most of the processes are involving pyrometallurgy, But apart from that, if we are still involving, if we wish to involve a hydrometallurgical operation, we can have parts of pyrometallurgy and hydrometallurgy coming into play, combined one after the other, and this can give us wide range of valuable materials. We will be continuing in the next class. Thank you.